Okay. In this slides, I'm trying to use this narration to show step by step for the system design.
To talk about design and the calculation of system, we have to focus at one particular air system. The tasks involved in this process can be summarized here by 5. The first one, and the most important one, is to determine the supply air. We did this before, basically, to find out its quality and quantity. Quantity is mass flow rate, and the quality is defined by the temperature, dry bulb, and then moisture content. Anyway, 2 points, 2 variables can determine the air state on psychrometric chart. All you can say is determine the quality basically means the state of psychrometric property. Then we need to size cooling coil to find contact factor, to find the latent central cooling loads at the cooling coil, which is shown here, estimated loads. And we also need to select heating coil. Right? Same, we need to estimate loads at those coils, heating coils. And for the heating coils, there's only sensible heat. Now, finally, the number 5 task is to find air states at each stage. For example, after mixing of fresh outdoor air and the return room air, or after preheater, after reheater, after cooling coil, and so on. So all those tasks are essential ones in the design calculation.
Now let's have a look of a common procedure of system design and calculation. There are a list of steps we need to go over. The first one is obviously to look at the weather, because the indoor condition is totally dependent of outdoor ones. So therefore, we need to analyze the weather of the location where the building is located, and then see if there are any potentials we can use. For example, prevailing wind in summer, we can think about the natural ventilation, and if there is excessive solar, we should consider shading and so on. Primarily here, we need to pick up right design conditions for winter and for summer. Then, second biggest task is to conduct a building analysis, checking if the building reflects the local climate, for example, thermal mass, solar control, and so on. And then second one in building analysis is look at the functions of the spaces in that building. So therefore, we can group all those spaces which share the same feature, such as functions as cellular offices and so on, share the same features of occupancy and orientation and so on. So therefore, we put them into one zone, and then another zone according to their own characteristics, functions, and so on. So we can make best of service for each zone for the quality and for occupancy. And then we need 2 charts, one schematic diagram, the other is schematic diagram. Schematic diagram shows all the elements, what to do, what heaters and where to put it and together, how they are joined together by ductworks and so on. And then schematic chart show us for the calculations, and they are used in parallel. And later on in the example, we will see how we use them together throughout all steps in this procedure. And here we need to mark all those key states on both the diagrams, on the schematic diagrams as well as on the segmented chart. So here I list 3 of those most important ones. One is outdoor state and indoor state. Outdoor state is based on design condition as well as the indoor condition we designed for comfort. And then we have ADP, apparatus dew point, which is very much depends on local the suppliers, the refrigeration systems. And then the 4th one is we need to determine the mixing. We need to think about how much fresh air is needed. And then we just provide enough fresh air and the rest will be return air. This is to secure the fresh air needed for air quality and minimize the energy spent on air conditioning. Then the 5th one is according to standard temperature difference for between supply air and room air, we can determine the mass flow rate. According to large number of studies, and then we have a recommendation. The temperature difference between supply air and room air is 8 degrees or less. Surely, larger the temperature difference, you can supply less flow. And then less flow means you can have a smaller fan and a smaller pressure drop and a small ductwork. So all beneficial to reduce initial investment. However, larger temperature difference also means poor quality. So the places close to supply can increase the larger temperature difference from the rest of the space in the room. So ideally, the delta T is maintained at a maximum of 8 degrees. We will see this later in the example. So look at the key formula is Q sensible heat equals mass flow rate multiply specific heat multiply temperature difference between supply and room. So the QS, Q sensible heat gain, is what we calculated based on what we talked about on Unit 5, the room loads. So therefore, we can calculate mass flow rate m dot equals the sensible heat divided by Cp and the delta T. From this, we can go on to find it out either by room ratio. From here, we can find out the moisture content through the calculation or through the psychrometric chart. Here, if we do it by psychrometric chart, we need to determine the room ratio line. And then through the psychrometric chart, we can determine the supply air moisture. So by delta T limitation, we can find the supply air temperature. And then by using this formula in step 5, we can find the mass flow rate. And by using room ratio line, we can find out supply air moisture content. So therefore, through this step 5, 6, 7, we can determine the supply air state, its temperature, moisture content, and also its quantity, the mass flow rate. Then we can go in backwards to find out after coil state. Here we use W, and to determine the contact factor of the heat exchanger or cooling coil And having done this, we need to check that out. Between the W and the supply air temperature, if there is a gap, we need to reheat it. Remember, from W, after cooling coil, going into supply, there is sensible heating. There's nothing can change in the moisture content. And so therefore, that is a reheater, the job for reheater. So far from step 5, 6, 7, 8, we are all dealing with summer operation. And then we can calculate the cooling loads, reheating loads, and something else. And then we can use this, repeat this number 5, 6, 7, and the W, and 9, 10 for winter operation. Okay, this is a summary of all the steps we need to go over when we do a system design and calculation. Now, let's look at how we work on the two diagrams, one the schematic diagram and the other the psychrometric chart. As we said earlier, the first one is to analyze the outdoor conditions. Now, suppose we have already got outdoor design conditions and we have already determined the indoor conditions. So therefore, these two states can be first marked out. Number one, we think the outdoor air is taken from the inlet and the controllers through the damper into the air handling units. And similarly, we mark the outdoor states on the psychrometric chart according to the dry bulb temperature and wet bulb temperature, or the dry bulb temperature or saturation. And then we put this latitude point, which is given from the manufacturer according to the chilled water temperature or the product of refrigeration plant. And surely we can mark it on this 100% full saturation, and then the temperature, very often it is 8 degrees. And then room condition, which we are happy to determine the 22-degree dry bulb, and then 50% saturate. Now, if you look at this system, so the room air being drawn from this extract fan, so they maintain the same state. And then here, by 3 synchronized dampers, we can determine how much they will mix with the fresh air. Now, let's for the sake of the discussion, we can assume 50% room air to mix with another 50% outdoor. So therefore, we join together this line, room air to mix with outdoor air, and 50%, and it is the middle. Now, look at this system, the mixed air taking over the heating coil, which is not working in summer. And then this carry on goes over the cooling coil. And then from psychrometric chart, it is a line taking from M over the ADP. So after this coil, the temperature will on this line somewhere. We don't know. However, we can find it out later. Now, let's look at room ratio line. Here we have two rooms. We pick up higher room ratio line and then draw this room line from R parallel to this line towards a lower part, which is to see to find out supply air temperature. So air supply temperature will on this line somewhere. And how do we determine where is the supply air? Is according to the regulations. The regulations suggest, as we said earlier, 8 degree maximum lower in summer. We supply cooler air into the room. So therefore, it will be 8 degree lower. So for the sake, again, explanation, we assume is 7 degrees lower than room temperature. So if we draw this line, dry bulb supply air temperature is here. All right. So here 22, 21, 20, and 19, 18, and 17, 16, 15. So 15 dry bulb temperature will be the supply air temperature for zone 1. And then if we happy this is supply air states, we can read out the moisture content. So therefore, we have determined the state of air or the quality of supply air to zone 1. Okay, the zone 1, because it's determined by the room ratio line L1. Okay, room ratio line 1. So this has been done. Then here is supply, okay, zone 1. And then if we're going backwards, means this we're tracing back towards the cooling coil and going through a fan system. So therefore, after coil will be from here to there, what you can see only going through this reheater. So heater doesn't change moisture content. So therefore, this line will be horizontal. So from supply S towards this will be a horizontal line, this one, to meet the M and ATW. So here, right, this will be W is off the coil here. All right. So this work, the temperature increase from TW to TS1 is the work to be done by the reheater here, reheater. Sometimes the fan and ductwork may raise 1K or 2K degree, and then that will ease the workload for the reheater. Anyhow, from W to S1 is this section. This section is contribution by the reheater, and the small one by the supply fan. Okay, increase the temperature slightly. So this is done for this one. And similarly, we can calculate the room ratio line for zone 2, which has a small number. And then similarly, we draw this parallel line that it goes through from the room condition and then meet this horizontal line. Means what? Means the moisture content doesn't change. All right. So this way will be supply air condition for zone 2. And then from this to this W is we're tracing back. And that will work by the reheater 2. Okay, so now having determined this supply air to zone 1 or zone 2, so then rest is to calculate the loads. The first load is we cool the mixture air from M to W. So that is shown on this schematic diagram. So from M to W is going over the cooling coil. And then cooling coil, there will be a cooling loads. How much? You can see from segment chart, cooling from M to W all the way. So we can read the enthalpy of M and then enthalpy change to enthalpy W. So the enthalpy difference when we calculate mass flow rate, okay, mass flow rate, and we use this formula, we can use the sensible heat gain in zone 1 divided by specific heat and the temperature difference from 20 room minus supply 15. Basically, this is 7 degrees, which is allowed temperature difference. So we can calculate the mass flow rate to zone 1. And then we can follow the same thing using the sensible heat gain in zone 2 divided by specific heat and the temperature difference between the room temperature and the supply temperature to zone 2. Here we find that it is 17 degrees. All right. Can you see this illumination line makes this horizontal have this is a state, the state of supply air to zone 2. So it only has 5 temperature difference, okay, 5 temperature difference. So therefore, according to this, you can calculate the mass flow rate to the zone 2. And you can see the zone 2 is mass dot 2. Zone 1 is mass dot 1. They join together, and then this, okay, going here, and then although 50% return and 50% go out, but when join the M, the 50% will join the other 50%, okay, going together in through this cooling coil. So although we sum M dot 1 and M dot 2 together, so they will have the same flow rate going this way. All right. So although they separate, but they will join by the same amount of fresh air. So therefore, the total mass flow rate going over cooling coil will be the same. So you can see the total cooling load will be mass dot 1 plus mass dot 2 multiplied, and so the difference between M and then W, okay, M and W. So this will be total cooling loads. There's another way to calculate this, is by calculate the sensible temperature change from this all the way down to the W. And so you have first sensible cooling loads, and then you can calculate the mass, the moisture content, swap to this moisture content. So you calculate the latent heat. So either way will do. But here, for the sake of simplicity, we can just show this is using the enthalpy. And this is the work, the system loads for a cooling coil. Let's calculate the loads at the reheater. So the load reheater is heating the temperature from TW to TS1, right? And the mass flow rate is here, M dot 1. So M dot 1 multiply specific heat, multiply temperature difference from the supply minus TW. So this will be the tangible heat load at this reheater. Similarly, the mass flow rate going to the room zone 2 is multiplying by specific heat and then temperature difference between S2 minus TW. So therefore, through this, we calculate all the system loads.
Now, this is a typical example of one air handling unit provide cooling and heating for 2 zones. Now, the air going into the air handling units comprises of 2 parts. One is 30% refresh air by mass, and the rest will be the return air. Now, the room condition is maintained at 20 degrees dry bulb and 50% saturation for both seasons. And air handling units consists of fresh air intake and a mixing chamber where the return air, fresh air are mixed. And there's a cooling coil and a fan and preheater and local reheaters. Now, in summer, outdoor condition is 28 degrees dry bulb, 21 degree wet bulb, and in winter is 3 degree dry bulb and saturated. It requires to draw a schematic diagram, and which is obvious. You need this diagram to help you to design a system. And normally in this kind of exercise, you need 2 diagrams. One is this layout, the other is schematic chart. So you need a very sharp pencil and set square and rulers to do this exam. So all the calculations include determining supply states for each zone. That means you need to calculate the supply air temperature and the moisture content. So two values determine the state of the supply air, and then you determine the volume in a mass flow rate or volumetric flow rate. Normally we do mass flow rate, and then we calculate the cooling loads and heating loads. Even in summer season, we need to calculate reheating loads. Right, now here are some steps. The first one, you have to calculate the temperature of mixed air. So we use M to represent the point of mixture. Now you can do this actually on the psychrometric chart. You plot the indoor condition and outdoor condition, draw a line, join them together, and then you plot the M, the point which you calculated from the first the equation you have here, and then draw the plot. Okay, you see that is outdoor and mixing. So one line, draw a line, and then you plot 14.5 is a mixing in the middle. Then you also find W is off coil, because it says 11 degree 90%, so you have this W. When you have these two lines, the 2 points, M and W, you draw a line, link them together, and extended it to meet 100% saturation line. Then you get a pressure dew point, okay, A. Then you use the calculation of room ratio lines. So that is room ratio line for one zone, and this is for another. Right, so therefore, from W after coil to any point on these two room ratio lines, the easiest way is to reheat. So therefore, we draw this reheating from W to meet the two RRL lines, the red airlines. And then this two actually shows the supply temperature for the two zones. Then when you have the supply temperature, you calculate the flow rate. So from the zone 1, the total sensible heat gain is 60. And when you from the chart, you find out the supply air temperature for zone 1 is 12.5. So therefore you calculate this mass flow rate going into zone 1, which is 6.19 kilogram per second. And use a similar idea, same formula, which is sensible heat gains divided by specific heat and temperature difference between room temperature and supply temperature. In this case, supply temperature is 14.5, and you get a 5.2 kilogram per second. So that is the flow rate going into the second zone. To sum these two flows together, you get a total mass flow rate, 11.4 kilogram per second. That is the total flow going through the air handling units. So then you find out before and after cooling coil enthalpies and multiply the total mass flow rate. You get a total cooling load for the cooling coil, which is 210.9 kilogram. Okay. Okay, and then you can calculate reheating, right? So you find out again after coil W to the supply temperature is 14.5, and then can you find reheating load for the reheater for the zone 2. Remember here we have to be careful because there's a 1.5 degree free gain, that is gain from the ductwork. So therefore the heating is not done by the heater, but actually obtained the heat from during the journey from air handling units to the zone 2. So therefore you take this out. Now for winter, again, you follow the same style. Plot point O for outdoor condition on psychrometric chart, and then draw line join the O and room together. Then you use the formula to calculate the temperature for mix the air. Then you go back to calculate the room ratio line. Here you use the figures to sum them together. No matter it's sensible heat loss or sensible heat gains, you get this 0.71 and 0.57, right? And then you draw the lines according to its sensible heat or sensible heat loss or sensible heat gain, and you determine the line going to right or to left. If there's a heat gain in the room, so the line goes to the left. If there's sensible heat lost, the line goes downwards to the right. Now, from the mixing, you draw a horizontal line to meet these two room ratio lines, and you will find the supply temperatures.
Okay, let's summarize what we have already seen, the steps or tasks involved in the procedure of designing an all-air system to operate winter and the summer. The first one, if we can skip designing the indoor and outdoor conditions, and it's the major work in designing a system is to determine the supply air, its quality and its quantity. Its quality has two variables to determine. One is the supply air temperature, and the other is moisture content. And the quantity is by giving a mass flow rate. Then we can determine the cooling coil and from the off-coil temperature and the application point, we can work out the contact factor. And contact factor is the figure we use to buy a heat exchanger. So we just tell the manufacturer what contact factor we want, and then after coil temperature and this, the application point, then we can buy a right size of the cooling coil. And for the same reason, same procedure, we can select heating coil for reheat for both zones. Now, when we consider winter together, so having decided the size for reheaters, the rest of the heating will be the work for the preheater. Having designed all the elements, the rest will be calculation, the system loads. Remember, in Unit 5, we did calculation room loads. Now this is a system loads. System loads means it comes from number of components. The number one operating in summer is the cooling loads at the cooling coil, and then the heating loads at the reheaters. And in winter, and we have 2 reheaters and 1 heaters. So therefore, they are a number of different parts we need to calculate individually. And then we needed to estimate the air state at each stages, the outside and the mixture and off coil and the supply and then room conditions and so on so forth. So these are the tasks involved in a design system. Okay, thank you very much.